discrete random variables, page 7. Number 9. During a season, a basketball player has a 94% success rate in shooting from the free throw line. In one match, the basketballer has 20 shots from the free throw line. Find the probability that the basketballer is successful on all 23 throws, at least 18 free throws, etc. Okay, so let's see. So the number of trials is 20 shots. Success rate p-value is 0.94. And then we just need to figure out what our x values are. In the first one it says successful on all 20 free throws. So let's draw our little distribution. And in 20 trials you could have between 0 and 20 successes. So in this case here they're saying what is the probability of getting all 20 in. So that would just be a PDF, right? It would be PDF with x equals 20, right? And the next one says at least 18 throws. So at least 18 means more than 18 and including 18. So it would be 18, 19, and 20. So what they're asking for in the last one is basically this region here. And remember that since binomial CDF cannot do right regions and can only do left regions, what you're going to do is you're going to say, okay, not 18 and above, we're going to do 17 or less. Okay, so what we're going to do is we're going to do CDF and we're going to do x equals 17, and then we're going to subtract it from 1. Okay, so let's do each of those. So in the first one we're going to do distribution, binomial PDF, number of trials 20, p-value is 0.94, x value is 20 out of 20, and the probability is 0.290. 0.290. Okay. What about at least 18? So to do at least 18, what we're going to do is we're going to find the probability for 0 through 17, and we're going to subtract that from 1. So we're going to do CDF, and then we're going to do 20.94, and we're going to do 17, and that gives us 0.115. So this region here, this left region here is 0.115. And then so if we want to find the other region, we do 1 minus 0.115. And that'll give us 18 or above. So we'll do 1 minus 0.115 gives us 0.885. So the answer to this one is 1 minus 0.115 or 0.885. Okay, and the last one, find the expected number of successful throws for the match. So the expected number, remember what we want is we want the number of trials times the probability. And this is in the formula booklet. If you look in the formula booklet, it'll tell you that the expected number is n times p for binomial distributions. So we take 20 shots and we multiply it times 0.94, and then we get a lot of free throws, 18.8. Okay, so that's the answer for the expected number of successful free throws. 11. How many ordinary dice are needed for there to be a better than even chance of at least 1 6 when they are thrown together? Okay, so that's like taking one dice and throwing it a bunch of times, n times. Okay, so this is also a binomial distribution, even though you're throwing a bunch of dice at the same time. Basically, you're using the many dice to simulate throwing the same dice over and over again. So how does it affect your chance of getting a 6, at least 1 6, if you have more dice? Well, it's easier, right, to get at least 1 6. So in order to figure this out, we're going to kind of work backwards, right? Because we want a better than even chance, which means we want a 50% chance of getting at least 1 6. Okay? So basically, what would we do here if we were going to do it with the calculator? We'll do binomial PDF, and there is a 1/6 probability of getting a 6, right? And n is going to be some number, however many dice we're going to have. And then the x is basically we want at least 1. So we want exactly 1 or more, right? So in this case, let me draw a little diagram for you. So we have a distribution which goes from 0 to something. Depends on how many dice you have to throw. And what we want is at least 1 6, which would be this whole thing except for this piece here. Okay? So if I was to do this without the calculator, I would say, okay, how do I calculate the probability that I would get 0 6s? And that would be, I would have to get not a 6, not a 6, not a 6 for every single one of my throws, and I would basically square 5 6 n times, right? And I would want to do this until I get 50%. So my question would be, when does the probability of getting no 6s equal 0.5? I mean, if you just have one throw, then it's way more than 0.5. The more throws you have, the closer it gets to 0.5. So how would we solve this equation? Well, there's a lot of ways we could solve it with the calculator, but one of the ways would be to take the log, right? But I think that's probably, you guys don't remember how to do logs maybe, so what I'm going to do is I'm going to put the equation into y equals 5 divided by 6, and then I'm going to put to the x, and I'm going to compare that to 0.5. I'm going to see when these intersect. So there's my function 5 6 to the x, and there is my function 0.5. And then to find the intersection, I do second calc intersect. And then I just hit enter 3 times. And the answer is 3.8. N equals 3.8. So that means I would need to do 4 dice. If I have 4 dice, then I would have a less than 0.5 chance of getting 0, and therefore greater than a 0.5 chance of getting at least 1. The way you would do that with binomial PDF is you would do second distribution, binomial PDF. Oops, not there. Second quick, get out of that. Binomial PDF. And then you would put the number of trials being like 2. And then you would put 1 6 here. And then you would put 2 here, 0 here. And then you would see what that is. And it's a little bit too big. We want to make it go all the way down to 0.5. So you would change the 2 to a 3. And then you would change the 3 to a 4. You see it's getting closer and closer to 0.5. It's not below 0.5 yet. And there we go, 0.48225. And so now the probability of getting 0 6s is less than half. And so then the probability of getting at least 1 6 is slightly more than half. And so you would need at least 4 throws to have a better than even chance. How would you do this with the table? You could put the bin PDF function here. You could do second distribution binomial PDF, and you would put trials x 1 6 x 0, and then this would put all the values in for binomial PDF, and you could see the same values we got when we did it manually. You can see that like once you take the number of trials from 3 to 4, it goes below 0.5, which means that the probability of getting at least 1 6 goes above 0.5. Okay, so the answer would be 4. 13. A new drug has a 75% probability of curing a patient within 1 week. If 38 patients are treated using this drug, what is the probability that between 24 and 31 patients inclusive will be cured within a week? Okay, so once again we have a binomial distribution. And since we have 38 trials, 38 patients, it goes from 0 to 38. And what they're saying is, what is the probability that between 24 and 31 patients will be cured? 24 to 31 patients. So they want to know this probability here. And so remember, the calculator is good at calculating probabilities that are on the left side. So we can't calculate 24 to 31, but we could calculate 0 to 31, right? That's pretty easy to do. And the other thing we would do is we would calculate 0 to 23. And then we would subtract the 0 to 23 part from the 0 to 31 part. Okay, so let's do the red part. What we're going to do is we're going to do bin CDF with trials equals 38, x equals 31, and p is equal to 0.75. So let's do that. Second quit, second distribution, and we're going to do binomial CDF, and we're going to put 38 trials, 0.75 p, and then we're going to put 31 to find the red region. Oops. The red region, it's going to be 0.872 is the red region. And the black region, we're going to do from 0 to 23. So we put 38.75 and we put 23. This is the black region. The answer is 0.0348 for black. Black region was trials 38, x equals 23, and p is also equal to 0.75. So what we're going to do now is we're going to take the red region and we're going to subtract the black region. And that will give us the blue region. So the blue region is 0.87 blah 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 minus 0.0348, which is 0.837. And we're done with this page.